big phrase, and there are a lot of words there, and so let's see what it means, all right? Let's start out here with some set which I'll call A, and let's indicate the set by the elements 1, 2, 3, 4, okay? And let's just make up some other set. Let's call it the set B, consisting of, let's say the elements 2, 4, 6, 8. All right, now, what I'm interested in is a set of all elements that are in both A and B. All right, we want those elements that are in both A and B. And what elements do you think we have that are in both A and B? And Bob says
2 and 4.
2 and 4. So let's indicate that with the set of elements 2, 4. All right, now, there's a special symbol that we use to introduce to discuss this idea, in which if this is the set A and this is the set B, in which we ended up with the elements 2, 4, the symbol that we use is this symbol here, and it's given a special name, and it is called intersection, I-N-T-E-R-S-E-C-T-I-O-N, all right? So the name of this idea, if I may write it down up here, has to do with the intersection of two sets, in this case A and B, all right? The intersection of those two sets, and it has to do with all of those elements which were in both A and B, all right? In both A and B. Let's look at another example. If this were example 1, let's talk about example 2 here, in which, let's talk about, in this case, the set of all x's, say, such that x is less than or equal to 3. And let me give this set some name. Let me decide to call it C, all right? And then let's decide to call some set D, the set of all x's, say, such that x is greater than -1. All right? Now let's make the graph of these two sets. Now if I made the graph of set C, right here, let's say this is 0, 1, 2, 3, 4. All right, -1, -2, -3, -4 in this fashion. Now, let's see, what's the graph of C going to look like? X is less than or equal to 3. The set of all real numbers x such that x is less than or equal to 3 is going to be what? And everyone says, Sally says? A heavy dot at 3. And the arrow going to the left, all right? And on forever, is that right? Now, right beneath it, what I'd like to do, and here's still 0, 1, 2, 3, -1, -2, -3, -4. What I'd like to do is to now make the graph of set D, okay? Right beneath it. And here is the set of all x's such that x is greater than -1, and what's its graph going to look like? And Brenda says,
an open circle at -1.
Open circle at -1. And a heavy line going to the right, okay? Now, what I'd like to do is to make a third picture, which is now the intersection of these two graphs. If this is the graph of C, and if this is the graph of D, I now want to make a graph which is the intersection of these two sets. And what do you think that graph is going to look like? First of all, here's a number line, -1, -2, -3, -4, in which we want to concentrate on these two graphs, in which we want to indicate the intersection set on this graph right here. And what do you say about that? Brenda says,
Put a heavy dot on 3.
a heavy dot on 3,
And an open circle
and
at -1.
an open circle at -1, and a heavy line between. Is that right? Does everyone agree with that? That this is the intersection set. If we gave this set C, this graph, the name C, and this name D, all right, this one would be what? C intersection D, which would be this graph right here. Is that right? Okay? In which it would be the set of all elements which are in both C and D. Is that right? The set of all numbers which are in both C and D, and the graph of that set would indeed be this graph right here. Okay? Well, let's see. Let's look at another idea or two here that has to do with intersection. Suppose we were to take, all right, let's make a picture in which here I have, say, a circle in which I will indicate by, let's say the set E, I want the set of all points inside this circle, okay? And let's talk then about some set, let's call this set F, as a set of all points inside this circle. And if I were to shade the set of all points inside the circle E in this fashion, and then if I were to shade the set of all points inside circle F in this fashion, what points do you think are in E intersection F? And what can you say about that? And where would these points be? Steve says
They'd be in the middle.
those points that are in the middle. And I think in the middle you mean these points right in here. Is that right?
Yeah.
Is that right? Okay, so that this set right in there, let me indicate this with this arrow, in which this is the set of all points in both E and F. Okay? E and F. These pictures are given a special name, named after an English mathematician by the name of Venn, V-E-N-N, and we call them Venn diagrams, okay? Venn diagrams. And here's an indication of those elements which are in both E and F, okay? In which we can indicate it in this fashion like this. Suppose I had another example in which I took some set, let me decide to call it some set G, consisting of the elements 1, 2, 5, 7. Okay, and now let's suppose we had some other set F consisting of the elements 3 and 4. Now, suppose I were interested in G intersection F, and what do you think we can say about this set? And Sally says,
The graph would be null.
yes, the graph would be null. That is, the graph would have no elements on it, certainly. What then can you say about the intersection of these two sets? What elements are in both G and F? And Ken says,
No elements.
no elements. And hence, if we have a set that contains no elements, we may indicate it in this fashion, which is another name for what set? And Chuck
The
says
empty set.
we may also give this the name of the empty set, in which we have used this symbol right here. Is that right? Okay. So, this has to do with this concept of intersection. And now let's turn to another idea. Well, let's call it Roman numeral 2, in which suppose I, again, were to take this set A, consisting of the elements 1, 2, 3, 4, as we have before, and let's take the set B, consisting of the same elements 2, 4, 6, 8. And now what I want are those elements which are in either set A, in this case A, or B, okay? Either A or B. Now what elements are in A or B, and if we were to write the set down in this fashion, it's either in A or in B or in both, which means it says in at least one of these sets. Steve says
1, 2, 3.
the elements consisting of 1, 2, 3, 4, 6, and 8, all right? Now, if we were to introduce some notation to indicate this, the symbol that we use is this symbol right here that looks like a U symbol, and the name that we give this is called union, U-N-I-O-N, all right? In which if we had to give this a name, it's the union of two sets A and B, all right? The union of two sets A and B. Now, let's look at a picture. Let's go to a number line in which let me introduce some set in which I will call it set E, say, in which, let's say it's a set of all x's such that x is greater than 3, okay? And let me introduce some set, let's decide to call it F. It's a set of all x's such that x is less than or equal to -1, okay? Now, the graph of the set E, all right, is going to look like what? Suppose here's 0, and here's 1, 2, 3, 4, 5, in this fashion. And what would that graph be? And Mary Lou says,
It is an open circle on 3.
an open circle on 3,
And a heavy line goes to the right.
and a heavy line going to the right, okay? And then if we were to make a graph of some of the set F right beneath it, in which here's the number 0, -1, -2, -3, -4, -5, in this fashion, say, -4, -5, in this fashion, 1, 2, 3, 4 over here. All right, and this, of course, on this graph, we had our negative numbers, -1, -2, -3, -4. What now would be the graph of the set F, the set of all x's such that x is less than or equal to, Jane says, an open circle at -1, and now this is less than or equal to, so I think you'd like to say a closed circle at -1, okay? And what then else can you say? A solid line going to the left with an arrowhead on it. Is that right? Now, my question is, here's some set E, and there is a set F, and now we are interested in the graph of E union F, in which we want the set of all elements which are either in set E or in set F. And Chuck says its graph is going to consist of what?
No elements.
no element in this set. Now notice we want the set of all elements which are in either E or F, and not those which are in N. So Bob says...
Closed circle and -1.
Closed circle at -1. Well, let's make a number line first. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5 in this fashion. Let me finish the number line first. And what do you say, Bob says?
Closed circle and -1.
A closed circle at -1.
Line going to the left.
And a line going to the left.
And an open circle at 3.
An open circle at 3.
Line going to the right.
And a line going to the right. Now notice, in this case, we want the set of all points which are in either the set E or the set F. And the graph of that set, we look at these two, in which notice it turns out to be those elements which are outside of that given interval. And Chuck, is that all right? Is that, in which we want those elements going less than or equal to -1, and x is greater than 3, as in this fashion here. Well, let's decide to call this idea 2 under here. This is number 1, in which this is, say, number 2. And let's then look at a third idea, number 3. Oh, let me take another example of which we have a circle in which we want the set of all points inside this circle. Let's decide to call this G, the set G of all elements inside of this circle, in which if we had to indicate it with some shading, let's say that it would be the set of all points inside of this circle. Is that right? And now let's say that we have the set H as the set of all points inside this circle. All right? And now what elements do you think are going to be in that set contained in G union H? And what elements are going to be in this set? And what do you think about that, Ron?
All the elements in both sides.
All of the elements in both circles. Is that right? Is this point in G or H?
Yes.
Is this point in G or H?
Yes.
Is this point in G or H?
Yes.
All right? And in which it's in at least one of the two given sets. Well, I don't think I want to shade it in any more than what I have here. So let me just indicate this in this fashion as a set of all points which are in either G or in the set H. Okay? Well, let's see what else we can do here with this idea. Suppose we had a set of elements. Well, let me make up another example. Let's talk about the set K. In this case, the elements say 1, 2, 3, 4. And now L as the set consisting of elements, what can we say in this case? Well, let me indicate 3, 4. Okay? Now, what is K union L as we have it written here? Set of all the elements which are in either K or L. And what then is that set going to consist of, Todd?
1, 2, 3, and
1, 2, 3, and 4. 1, 2, 3, 4. Give me another name for the set 1, 2, 3, 4, as we have it here. And Ken says,
K.
that's another name for K. So notice that K union L in this example is equal to K. All right? And in fact, we're going to say a few words about that in just a second. Well, let's then look at a third big idea in which, let's look at an example. Perhaps this is a good place to start here, in which we have this set K. Let me repeat it. In which we have the elements 1, 2, 3, 4. And now let's take the same set L consisting of the elements 2 and 3. Okay? Now, is every element in set L also in set K? And Sally says, yes. All right. And I think if I were to write this set 2, 3, and if I were to write the other set 1, 2, 3, 4 in this fashion, there's a symbol that we introduce that tells us that every element in this set is contained in this set. And the symbol that we use is this little, what looks like this U symbol on its side, but it's not quite that. And we call this symbol a subset symbol, S-U-B-S-E-T, all right? Every element in set K, or in this case in set L, is in set K, all right? So we may write what? K, or rather L, is a subset of K in this fashion. Is that right? Okay? Because every element which is in L is also in K. By the way, suppose I looked at the set K, and is K contained in K? Is every element in set K also in set K? And Bob says, yes. Yes. So I think we can say that every set is a subset of itself, all right? every set is a subset of itself. There's another agreement that we make, by the way, that I'm not sure that the book makes it at this time, but most mathematicians will make this agreement, and that is that the empty set is a subset of every set, except itself. All right, and indeed, in this case, let's just indicate this by, this is a question which in both cases we will answer it yes. Now, perhaps it's easier for us to accept this statement that K, every set is a subset of itself, and perhaps it isn't quite as obvious for us to accept this statement here. But it's a question of our simply making this agreement that every set, the empty set rather, is a subset of every set except itself. Because then, of course, if we're a subset of itself, then it will no longer be empty, which I think we can get into later on sometime. All right, now, let's look at two pictures again. Perhaps if I were to make a circle, say, in this case, so let's say that we have the set A, and let's say that in this instead of all points inside this circle, this is a circle with set B. All right, what can we say about B and A in the picture that we have drawn here? And Bob says
B is a subset of A.
B is a subset of A. Does everybody agree with that? In which B is a subset of A. Now, in the case that we have here, again, what can we say about A union B? What would A union B be equal to in the picture that we have here? Brenda says this is equal to the set A. Does everybody agree with that? Okay. What do you think you can say about the set A intersection B, as given in the picture that we have here? A intersection B. And Mary Lou says this is equal to the set B. Is that right? Okay. And I think there might be one other case, one other picture that we can look at. Suppose I were to call this idea number 1, and then let's say that this is idea number 2, and let's take this as our idea number 3, and I think perhaps we can have one other picture over here. Oh, again, let's take this set inside of this circle as the set C, and let's take some other circle which happens to be outside of this case. Let's decide to call this set D. All right? Now, as given here, is D a subset of C? And I think you would have to say no. What then, are there any points in common to both C and D? And what, in other words, if I looked at the set C intersection D, what is your conclusion about this set? C intersection D, Steve says, is equal to the empty set, the null set. And there's a word that we use to describe this, and it is called disjoint, okay? D-I-S-J-O-I-N-T. In fact, there's another word that I don't think the book mentions, another phrase, a fancier phrase, in which they are called mutually exclusive. E-X-C-L-U-S-I-V-E. It sounds like a sociological phenomenon, doesn't it, rather than a mathematical one. But if two sets have no points in common, that is, if their intersection set is the empty set, then we may say that these two sets are disjoint or are mutually exclusive. Okay? Well, let's see. I think there's just one other idea that we would like to look at. Let's come back to one of the first things that we did over here. Let's say that we take the set C that we have written as the set of all x's such that x is less than or equal to 3. Okay? Now let's take the set D as the set of all x's such that x is greater than negative 1 as we have it written over there. Okay? Now, if we were to use the notation C intersection D in this fashion here, all right, I may write down the set C as the set of all x's such that x is less than or equal to 3. All right, and now this says intersection, so there's intersection, and it's an equal symbol, so indeed this set intersection the other set of all x's such that x is greater than negative 1. Okay? In which this is a set, and this is a set in which this is the intersection of those two sets. Okay? Now, I may also write this in one set notation in which I can talk about the set of all x's such that x is less than or equal to 3, and, now here I'll use the word and, x is greater than negative 1. Now notice I will not use this set symbol inside of the set brackets, okay? I must use the disjunction, our conjunction, remember, which is the word and, between two sentences, okay? Now, of course, you and I have come up with another way in which we can write this disjunction. Instead of using the word and here, conjunction, instead of using the word and, how else may we write it? Something that has to do with between, in which x is between two numbers, and in this case, What can we say about that? Huh? Anybody? Where is x between? And Todd says x is between?
It's between between 3 and...
All right, one way in which we can write this is to say what? X is what? Greater than -1, right? And less than or equal to, what may we write here? 3, is that right? Okay. X is then between -1 and 3, in which we will include the element 3, but not the number -1. Is that right? Okay. Now, I think we can repeat everything that we have said about two other sets if we made up some other examples, in which here is some set E. Let's make up some set E as the set of all x's such that x is greater than 2, say. Okay? And let me write it over here. F is the set of all x's such that, what, x, say, is less than or equal to -3. Okay? Now, if I wanted to talk about the set E union F, all right, we may write this as the set of all x's such that x is greater than 2, union, all right, in which it's outside of our two set brackets, the set of all x's such that x is less than or equal to -3, all right, which is equal to, now if we decided to write this all in one big set bracket, what word must I use inside here? And Ken says 4, all right, the set of all x's such that x is greater than 2, or x is less than or equal to -3. Now notice with the use of the word or here, we cannot put the number x between two given numbers. It has to be outside of some interval, all right, outside of some interval. So let's decide to call this idea 1 all the way down to here. I think there's one other idea that we should look at. For example, in the set E, we have x's, the set of all x's such that x is greater than 2. Is that right? For example, suppose I took the element 4. Does 4 belong to the set E? All right? Now, the symbol that you and I have been using is this little belongs to symbol, in which 4 belongs to the set E. Okay? Now, if I put brackets around the element 4, in which is now the set consisting of the number 4, and now here is the set E, what symbol must we use here? And Mary Lou says the subset symbol, okay? The subset symbol. And of course, if we looked at the set E, which is x is greater than 2, suppose I took -1, you and I know in this case that -1 does not belong to E. And if we were to put this in set bracket, -1, and here's the set E, what notation do you think we can use here? And Bob says
Subset with line through.
a subset symbol with a line through, which indicated that -1 is not a member of the set consisting of E. Is that right? The set consisting of the element -1 is not a subset of the set E. And all of this, and if we had to give a name to this, let me just indicate this by notation, all right? These are various forms of notation that I think that you want to get used to. Well, let me give you your assignment for next time, and I think that's all we need to do for today.